So the last time we talked about the Landau's molecular theory, where there is no interaction in an environment, but the theory can be just used to describe by using so-called Landau parameter, and then just the behavior square from the ideal. But today, so this is the main part, main concept of the theory of superconductivity. Okay. So today, from today and even like the next week, is the main content, one of the main goals of this lecture. Okay. That's 19. So before we see a crucial consider the following problem. Let's consider the everything we consider is a permanent particle from now. And then Cooper considered the points and there is a pair. This is the family. Okay, 11. And this is the family circle. Okay. But there is excited states in with momentum k and speed up, and really on top of it, you have a minus k and speed up. If you consider such a pair, consider such a pair, it's right above the momentum. So minus k and this is the and also so Z R attractive forms. Interaction. Okay, and then so I mean, so the assumption. So this is assumption. Assumption. So two electrons on the center. Two electrons with the up and then get down, and then K is right above is the K minus is very tiny. It's very tiny. So this is the current surface, and in current surface, you have a Fermi momentum, and then this K and this K minus K is the really right above the Fermi moment. So this is assumption. So assumption. And then you can solve it. Whatever, Schrödinger time equation, Schrödinger equation, and then Cooper showed, I think it's 55. Cooper showed, there's one bound. Oh, this is go Cooper. So before BTS, so assume the two grouping, so the two electrons near Fermi surface with the opposite momentum of the spin, and they're subject to infinitesimal attractive interaction. And the following. So that's what we are going to show first before BTS. Okay. So the Schrödinger equation is of course given by like this, but and then this way. And equation like this way. And we assume that the star of R2 can be written in terms of this is infinitesimal small attractive interaction. So the wave function is almost like can be decomposed by the Fourier transformation for this fragment. If you black out when you hear, you can just have a black base when you hear. You can have this again once. That's this first. And sorry. So that of course, so this guy is just an H button per divided two. I don't use first up. So that's what you get. And now so we will decompose this in terms of the center mass. So we decompose this one. So we decompose this plane wave. So this is plane wave into the point e to the side. Have the and the center of momentum, center of the coordinate, and the object. What you write down? Have the is kilowatt plus and capital R is R1 divided. Okay, and then small k we came out and R R1. So this is the so the first part is called center of mass. Center of mass momentum and the center of mass coordinate, and this is the relative momentum and the relative moment. Anyway, so if you have the two particles, R1 and R2, and then just move. So move whatever direction K1 and K2. So you can have the, so you can just consider total, I would say two average position of the essentially the R, like this way, and this has the whatever momentum capital like this. That's the center of momentum. And usually you can ignore it. And then that's what I'm going to do. So I assume capital K. So I just interested in the ground state. So therefore, you don't need to consider the center of mass motion. So capital K should be. That's what I'm going to do. And then okay. So then what is this? Then I think what's going to happen is that here, if you write down everything into in this momentum, so this one can be just written like a G. That's right there. That's more. Okay. And then let first assume the capital K from 0, and then this can be written like this, like K star. G2 and plus one of the B is the volume of space-time, G2 and prime, and then capital the prime, G2, and that's in terms of so in terms of momentum, right, we're like we assume that in UK there will be felt in Canada. Okay, came out of the problem. Great translation. Great translation. Okay, so that's what we want to consider. then if you assume capital K, so capital K equals to 0, and just write down this capital K equals to 0, and the prime is equal to small k is like this, and this equation, you just reduce it to the following. Plus 1 of me, 1 of k, you Thank you. So this is concerning your question. Okay. And then, so the second, so this is the second assumption. So second assumption. Equivalent K prime is equal to minus G and 0, where so this is second assumption. And this H bar of omega D is called, does anyone know what it's called? So H bar omega D is called divide energy. So divide energy. So here, so you can have a DEF, and then so this length is essentially H plus omega D divide energy. So if the K momentum K is inside this shell, then the potential is minus G. Otherwise, you get 0. So that's the second assumption. So divide energy is the thing. I mean, this is the so H bar omega D is the highest excitation energy. So last time I told you that it's the beginning of the lecture. So I told you there is some lattice. If you have a lattice of the and you have a plus sign in the lattice here because of the nuclei equals the nuclei, right? And then the electron enter here. Electron enter here. So this lattice is somehow attracted by how to say charge attraction, electric attraction, and this lattice becomes a bit small. So it becomes a bit small, and the net charge around here becomes positive. So therefore, another electron wants to come here. So if you have used another electron, its attractive net charge is plus into this lattice. That's what I explained. I show in even video at the beginning in the first lecture. If you want, I can show you that later. And that is in fact will create this utility. And this attraction is called formula. And this attraction has a there's a maximum excitation energy. Because I mean, roughly speaking, so there's an L here. If you have an L here, it's the divine energy. The maximum energy is roughly 1 over L. 1 over L. So if you have lattice length in the L, then energy you can get is maximally 1 over L, roughly 1 over L. You cannot get like you cannot get high. I mean, if you want to have a higher energy, the lattice length needs to be smaller. Otherwise, I mean, you cannot get. So that's the divine energy. It's called divine energy. Divine energy. And usually we think that it is energy to divine energy. So this the K and K prime, we are interested in between Fermi surface to the plus H plus divine energy. That's what we are doing. And then we will try to solve this equation. So then let's write it down in terms of so if you assume this potential, so then this Schrödinger equation can be written as follows. So now it's just constant, and we just need to sum over K prime, where the is from F is from K prime, and then is from F H of omega D, X prime is K prime. So that's the summation range. Summation range is equal to E and F of K. So that's the Schrödinger equation. Oh, sorry, I missed the F of K. So that's what you get. And then you realize so this one, this part is independent of the so this part is independent of the independent of K. So independent of K. So therefore I call this one is equal to C. So then what you get is that E is from K. F of K minus C is equal to E times F of K. This means that F of K is equal to C over 2 from K. It's very simple way of solving. Any question? Is there something strange? Is something strange? Is it okay? Okay. So now we can solve this with C, because I mean C is equal to by definition G over E sum of K prime. K prime is in this shell. So K prime is inside. K prime is inside of this shell. Okay. And then F prime. And then this is our link. And K prime is inside of this shell. And F K is real to show. So now we just plug up on E equal to K prime. What I get. And then see, we can see now from C And then this will give you 1 is equal to G over P. Like this. So now we want to so remember that it's shown here. So this guy is the eigenfunction. So eigen of that wavelength. And if the system, so if the system in the finite size volume, finite size volume B, so volume B, so of course epsilon case is discrete. And then, so if you write down that this, so this one means that the G over B is equal to sum of K prime, and this one is and the bottom is from K prime minus portion. And K prime takes a discrete value. And then you can just write down so this is the sum of the and then so you can consider this this is the sum over epsilon k. So here you have the you have a 2 epsilon f. You have a moment, and then so you have the so one is sum of this is sum over one of the 2 epsilon k. Okay. And then, so here you have the this kind of potential you have, and also you have this kind of potential. And then also, if you have another eigenvalue of a little bit above, which is k, you can have another potential like this. And then here you have another potential like this. So now, so you need to sum them up everything. So you have another eigenvalue, and then you have like this way, and then you have like this. Like this. And if you sum them out everything, so you have to sum them on all k. So then what you have is something like this. So like this way, sorry, maybe most likely like this one. And then here you need to interpolate in between. Interpolate in between. Like this way, interpolate in between. And this. So the potential becomes like this. So at each k, which is which is the eigenfunction just one way. So this one square plus square plus appropriate normalization. So 2n like this way. And then just looking at only like that's the K1 minus K2 part. Looking at K1 minus K2 part, and looking at each eigenfunction here above the Fermi energy. We have like this is the first extended one, second extended one, third extended one, and you sum them up all the one over 2 epsilon k minus e. Then it becomes yellow like this. And what we want is to find a solution of this equation. So then I think what we need to do is that you just look at the intersection between them. So this is the Shigeoba is equal. Okay? The intersection appears in here and here and here and here. Those are solutions to this equation. So the solution to this equation means that the solution to the Schrödinger equation. And the important thing is that so these points are all above 2 epsilon. Correct. However, this one is here is the less than 2 epsilon. So this E is capital E is less than 2 epsilon per reaction. So this means that there's the energy. So if you solve this Schrödinger equation, is the energy for these two electrons, total energy for 2 electrons, which is, so this means that if E less than 2, the 2 times fermion energy means that the distance is the bound of 2 electrons on the bound. But so if there is a free, there is no interaction U. If there is no interaction, the max, so the 2 electrons can have energy. If you consider the K is inside of this equation, the lowest energy is epsilon F. So Fermi energy and if there is 2 electrons, the lowest energy is 2 times Fermi energy. But so the energy now is less than that, which means that it forms the bound. So this is called so this is Cooper bound. So this is called Cooper band. It's very simple calculation, but it's very useful. And we will see what's going to happen. How does this so we're interested in how this difference between so this is the delta, which is the Fermi energy mass E. So what is this? I go delta, and let's compute this one. to compute this one, so suppose so b goes to infinity, and we use the vector function. Then this equation, if I wrote above there, can be written above. So 1 is equal to g and divide machine, and then g sometimes it's sometimes. So this equation is equivalent. This equation is equivalent to both intensity, and then it's so k is normally written. So suppose this is a function of L, and to do the summation, you just insert density function and just integrate all. Okay, and suppose we did the shower is thin enough, we can assume that the d is some prime, almost like that. Suppose so this shell is thin enough. This is thin enough, then we can assume it is some prime. It's roughly some depth or match. And you can just perform the integral, but the distance is roughly g from f divided by q, and log q is from f plus h and d minus e is from f like this. What's the and then you can compute from here by so this is equal to g times d f divided by q log e plus 2 omega omega d, and this is delta and delta. So delta is the line we divided. And from here, we want to just compute delta is equal to what? Okay. So this means that the delta plus h omega d divided by d is equal to e to g f divided by d. And then from here, delta is equal to h omega t divided by e to g d. Sorry, I think I told you wrong. So this should be ordered. It should point me out. Plus one. Okay, and then this is roughly speaking, suppose if here suppose assumption is G and D. Is correct. Okay. Okay. Good. Okay. So that's the energy difference between this bound state energy and the T times permanent. Is that okay? Is everything okay?
The denominator minus 1.
Denominator here. Sorry, what are you talking about? Which denominator? This one?
Minus.
This is minus. Is it watching? Okay. Maybe you might type it. Okay. Anyway, so the approximation doesn't matter. Okay. Okay, so the first thing is the bound state. State. So this bound state for any G. Any attraction. Number two. So delta is the exponential normal and bias. Okay. Number three. This is the most important. I mean, of course, everything important, but this so this binding energy here is the so binding energy delta cannot be obtained by calculation theory. So here, if you expand in terms of G, suppose G is very small. If you expand into G, it becomes something like this one, GD plus whatever, 1 over 2 factorial, and then this GD square and so on. Okay? Okay? But if G is very small, this expansion does not fall. Okay? I mean, if you do the test, I just do the Taylor expansion. But if G is very small, this kind of expansion does not give you any approximation. So therefore, I mean, G can be understood as coupling constant of the theory. But even if it's small, you cannot have like this kind of expansion. G squared plus second plus dq. So this is for conservation theory. But this kind of expansion cannot be applied to compute the. So therefore, this is beyond perturbation theory. So it's going off perturbative effect. So this is something called non-perturbative. quantum effect. This suggests okay. So those were the characteristics of this Kumo case. So that's the very important property of the Kumo. In particular, we consider something like it's called S-wave Kumo case. Here we assume that the wave function of Kumo pair of Kumo pair. I call it psi. R1 minus R2 is invariant. So this is R. I call it R. If R goes to R, R is minus R, and that so we don't assume any how to say. So it's really spherical symmetry. We assume that spherical symmetry. Symmetric. So therefore, this is called S-wave Kumo. So S-wave. I mean, if you assume that the different assumptions, so like you can obtain the L or whatever P or P wave Kumo pair and so on. But for the sake of simplicity, I'm not going to consider such a case. That's one thing I want. Any questions at this moment? Any questions at this moment? So what they find is that even though electron has an opposite, so because of even though the electron has the electric charges, therefore it's hard to imagine of the form. The electron has the electromagnetic repulsion. Even the so, but taking account into attractive force interaction due to quantum or lattice effect. Hold on, the lattice vibration. Due to lattice vibration, the one I already raised. Using the form, the form, Asian form, form of balance. That's what Google found in the loop. Okay, that's what Google found in this calculation. Okay. Any questions from? Okay, so that's from there. The BCS starts considering so-called largely for impedance. Okay. So now here. So let's talk about this. So what we still consider upon for the wave function of state is the actually condensed state of this Superconductivity. Superconductivity. So this is a complex ether. These are the so this can be understood as follows. So this is the opposite. So ether creation operator of the electron. And then they have the opposite charges. And of course, they have the opposite momentum. And then and the speed. So this means that so you just create the pair of Cooper pairs for each momentum k. And the vacuum, so the wave function is the actually condensate of the Cooper pair with momentum k. So with any momentum. But the k is around this initial. So the what this also is the state is a condensate state. Condensate of Cooper pair. So the state is a condensate of Cooper pairs. And then what they try to do is try to minimize this polynomial with this case. So when the problem is that minimize this energy, where Hamiltonian is given a problem. So this is the where CK is the Epsilon K constant. CA is the kinetic energy measured from, so this is the energy measured from chemical measurement. Essentially, I mean, from K minus mu means that they consider graph chemical sample. This means that so here we just have the this is the just kinetic term. This is kinetic term. And this is the interaction. So this is called VCS time function. So VCS considers point. Okay, so this interaction is that you create this is create a proof of data, creation of the proof of data, and this is annihilation of proof of proof. Annihilation proof of. And this somehow interact in this with this induction. That's the for BCS. And so this term is for S-wave superconductivity. So if you try to consider the other like a spherical, it's not spherical symmetric and so on, so this term needs to change. But I think for the sake of simplicity, we only consider the simplest interaction of in singular. Yeah, I mean this sigma here is the sigma is plus minus one plus minus in the input. So the problem is if you consider this such a state, the constant proof of state, and try to minimize this energy under this handgun with this handgun. So that's what we did consider. And there are lots of approaches to consider this one. So one would be again what we learned last time, half rate. So this is essentially perturbation theory, essentially equal to perturbation theory. So last time I introduced so-called Hartree-Fock equation, and then we try to recursively solve this Hartree-Fock equation. Through that, we will get the through the process of trying to solve the Hartree-Fock equation, we encountered another parameter. That's what we encountered last time. This one we can do that. Actually, we can do that. That's actually VCS did. But this is complicated. This method is complicated. I mean, I can do that, But I mean, if you write down all the equations, I think you will get lost. And so I think, but the simple approach is for the so-called mean field approach. Mean field approximation. This is one thing. So I would take this approach because I mean, if I use this arbitrary equation, the things are much more complicated. And if you write on a blackboard, it's got to be forever. So I think I prefer the simpler approach, and then most likely students also prefer the simple approach. Okay, to do that, so essentially what we need to do is use the mean field approach. We introduce so-called order parameter. Of superconductivity, which is delta the B zero sum over A. And note that so this expectation value, with respect to so this phi. So here the state is the has a condensated Cooper pair like this one. Condensated Cooper pair like this. Then you can consider this expectation value to be non-zero. If it is just vacuum, it's just this annihilation operator analyze vacuum. So C just analyze vacuum. It's just this. But now we apply lots of creation operators here. Therefore, okay. So this can be understood. So this can be understood as expectation value. So this is expectation value that annihilate one pair of one Cooper pair. And then this delta, since this is not Hermitian, so therefore this is complex number. So this is complex number. So we just have delta is equal to delta E equal to okay. So this sometimes is called superconducting state. Okay. And what is a mean field approximation? So mean field approximation is what? If you have operator O, and you have operator O, operator 2, then we just do the following thing. So you have operator O minus delta O1, and the operator 2 minus O2. write down like this way. You will see the approximation. It doesn't do it. Okay. And then just expand. So if you expand it, you have over 1 or 2 plus over 2 or 1 and plus minus over 1 or 2. So this is the case. And then we assume that the mean field approximation, the fluctuation of the O from the maximization value is very small. This is very small. The fluctuation is very small from the exponential value. So that you just ignore this and you just consider the O1 or 2 plus O2, sorry, O2, O1, and O1. That's what I'm going to do. You just apply this one to this. And then for me, O1 is equal to the prime dagger up to the dagger, and then negative or minus the prime. The O2 is equal to B plus T minus K negative. And apply this. So the output is this part. And here let's come to this one. Yellow part. So we won't get out by EP approximation. So this can be written as the time minus the time lower than minus and then so, unfortunately, I have here minus 3. Minus. Then plus k prime. Okay, the k prime, minus k prime. And then this alright, I think this should be better. Sorry, I think it's okay. Okay, and this thing. And then you have a two. And then C minus K on C K up. That's much approximation. And plug this way to here. Before plug that into here, you have to use this one. So we already know that the delta is equal to this order parameter is like this. You can apply it into here and also here. Okay. If you do that, so this Hamiltonian. This Hamiltonian can be written in a form. So the kinetic term is the same. Okay. Okay, is it okay? So here you just stumble over. So this one you get the double picture. You get the double picture. Also, you get the same thing for this dagger part. Um, and we try to diagonalize this. And this is exactly what you did in homework one. This is exactly what you did in homework one. So just revise everything in terms of okay. And first, let's try to rewrite this one. So the kinetic term is something like this one. So this is sum over k is ck and ck plus Pythagoras ck plus ck ck Pythagoras down and the ck up. This way. And this is equal to sum of k ck Pythagoras up. This is minus e k down. Sorry, I told you no. It should be on the same. Plus, is it okay? So here you just use the fact that the singular k, whatever, ck is equal to 1 minus e k. I just use the computation ratio, anti-computation ratio. And you just flip the k to minus k. K to minus k. Is it okay? Is it okay? Okay, so this is the genetic component. Then the plus interaction, which interaction, and then plus H research. And if you write that everything together, this can be written as follows. So this can be written the reason why I put the minus sign here is that here you have a minus sign here and a minus sign here. So therefore, to write that everything together in terms of this, like the inner product with vector, matrix, and vector, and so on. So you need to swap here to minus here. And this, the alpha is not important. Anyways, the alpha, so this is already, you guys get for actually, that's the reason why I did this, this probably to follow for. So you can understand very easily. So the alpha is equal to the alpha square over here, and then so we will drop this and so we will ignore. So it must follow. Ignore this. So it's just I mean constant shift of the ground energy. So that it just shifts of ground energy. So and try to diagonalize. So try to diagonalize this matrix next to it. Try to diagonalize this matrix. So and then we use the volume. So this is the plane up. We minus A up. Sucker. So 3 and B and B. Okay. Okay. Where so the 7 BPS squared plus BPS squared is equal to 1. So this means that so if you establish this view, you target the equal to universe. Okay. And if you use this transformation, it's easy to show that the satisfy the standard computation relation called even HK. So if that were right. So this is a good exercise to do. And other which means that the data is equal to C. So this is the whole treatment. So then, if I easy to do, so that one, I call it this way, it's equal to H hat. Then, so it's H is equal to sum over k into a factor k, and you transpose h hat u then into k, and the k factor. Okay, and this is equal to, and this is equal to k 0, 0, okay, I already erased delta. Delta is so I just erased. For the EK is given by square root EK plus delta. Okay, so bullshit. Um, okay. Okay. Maybe I can. Sorry, maybe I told you I will ignore, but start. So if you keep this one, okay, let's write down like this. Sum of k, ek, k dagger, and k plus ek dagger plus delta e. But if you just use the potential B, you have a dagger k plus dk dagger dk plus the delta E prime, where then delta E prime is equal to delta third of E0, the sum over k dk. So this is the result. Okay, it's very simple. Okay. So the outcome, so this one, K and BK. So AK and BK are the linear conditions CK and CK dagger, D and C dagger. So this AK and dagger and BK dagger can be as a creation operator of quasi particle space. Quasi particle in superconductivity. Superconductivity. Okay, it's very simple so far. And then we will see the consequence of this analysis after the break. Okay, let's take a break. Okay. Oh, sorry, I forgot to record my lecture. Sorry about that. Maybe only second half.
基本假设它是这个，就是可以对变这个就是上台面下面的讲，上次。
Even so here, sorry, this is dagger. Yeah. Yes. Well, it should be the same. Oh, yeah. Now I remember. So we just have so this differential is the outcome is not like B zero. Something like that. B is the constant and it's like a speed. Yeah, I don't remember. And this way the differential is B zero in some of the side is yes. And the side is good. Right? And this side is the product of some U and B and C dagger and C the dagger. I don't remember one of them. And C dagger. Yes. On the other hand, here you have if you conjugate it, it's just the backing of product of U plus B dot. B K and C K. Yeah. Okay. And then here you have a so it here is the product of all possible K, right? Product of all possible K, right? Yes. And then if you act this one, I mean you have some computation with the right hand side. But even if you have a dagger, you have a computation with the left hand side. So it should be the same. Use the if you use the permission. But do you understand? Do you understand what I mean?
So the conjugate of their part is
Sorry, I don't. Feel like this sheet. No.
It should be yeah.
Well, shouldn't this should be so hard?
Yeah.
Where? This is?
It should be doesn't have down small.
And no minus.
And then variation.
Yeah, you're right. Sorry, so what is the long? So this is star.
Yeah.
This is star.
No minus.
Here?
Yeah, minus.
Oh, you're right. You're right. Okay, I think you didn't just have it. Sorry. I think I should. You're right. Yeah, okay, I will correct it at the beginning. Thank you very much. Thank you.
就是错，要不应该是有上那个工作是下次。
啊。You're right. You're right. It's reading my lecture. But here is. Right, or right. So I put the data to the delta to the real. I just assume delta to real.
Sure.
For the sake of it. Yeah, I said the data is and also, yeah, okay, I'm not sure. Oh, okay, okay, sorry. I think I should mention, yeah. But, and also here, this both are minus. Both are minus. The function is fixed. The only thing the other one didn't have the partner. And then this one here, all the pages show and that was without it and the first. Thank you very much.
我还没写。
这个部分它是这个技术后前面是这个产生的是叶片，然后掉的是这个但是中间也是火候，还是假的。我也是，我也是把这个看明白，就是原来这个地方就是改成 产生电势夹后，然后对应了一下之后出现非常不好的例子，因为这个反射影响，因为那个电离子它是反射影响。哦，这个反正把这个球本拆成2块儿，然后对，就感觉这样子好啊，对，就跟你和你不一样，哦，对，感觉我是。有些时候在讲这个就先进的，然后你就待会儿再讲这个有点高。下面一个戏，戏。
哦。这个非常明显。Okay. Yeah. So this student pointed out that the take wait, I need to report that. Okay. Okay, the first half of the recording is missing. So anyway, you know, yeah. So sometimes this happens. So I mean, if you see that this recording is not, I guess the recording just to remind you. I think somebody must have already noticed that. So, otherwise, or maybe not. Okay, so the download I define is the B0 sum over CA is the divided and then CK C minus K down to CK up and leave. So that's what I define. And then here what I did the mean field theory here. Yeah. So mean field theory. And this one. So strictly speaking, this is this part delta should be delta star because this is the coefficient value delta star is something like E field sum over the same and C K other and C K is minus K down is 100. It should be, so as I mentioned, it's delta is a complex number usually, because it's not Parisian, and this is a gate actually. But for the sake of simplicity for the calculation, assume delta to be real. So this is the assumption. So I just write down delta is equal to delta is but I put the status in zero as assumption. Because I mean the calculation is very similar even if you use delta star here, but I mean it just becomes simpler. Calculation becomes simpler. Because if I use some complex number, if I don't use the assumption, when you do this Bogoliubov transformation, I think you need to include some like a I stay around here. You need to around stay here. And also, I don't remember the detail. Yeah. And then here you need to slightly modify somehow. I don't remember where we need to gently modify. Yeah. But in any case, so in the calculation U of P or somewhere else, you need to modify it slightly. But to avoid complexity, I just assume this is the case. Then delta star is equal to delta other function. This is our function. I mean calculation is similar. And I did negative sign before. It should be negative sign here. So that it becomes partition. Is it okay? Sorry about it. And then if you do the calculation, you will get this. Yeah, yeah, everything you need to, so I think so if you do the assumption, the statistic, so you have to use the nomenclature and so on and so on. Anyway, so the calculation becomes a little bit complicated, but to avoid complexity, to keep the simplicity, I should put this now, capital delta to be real. What's the assumption? Okay. Is it okay? Thanks for pointing me out. Okay. Then I will be right. Okay. So let's first show the how the overcome the delta decay. So delta versus temperature. So the next is with the autoproduct, how autoproduct behaves with respect to temperature. To do that, so we recall this A target K. So this is the numbering operator. So numbering operator for this quasi-particle for A. As I mentioned, this A and B are the some gradient coefficient of this, let's say, rich annihilation for vacuum. But in terms of this, this BCS, so this means that, okay, so it's better to mention before going that. So in BCS, A, K or B target, and BK target are better operator. Operator. Then the so that's okay. So here the free diagram became better in vacuum, but now so we consider the condensate of Cooper pairs. If you consider condensate Cooper pairs, this is A and B are a better creation analysis. So we should use this. So then A became better. Okay. This is the numbering operator, and we take better with the K. So this will satisfy the Fermi distribution E to K. And I call it about and then so delta equal to the sum over K. K, 1, K, up, and this is equal to the sum over K minus K. Okay, you take it, and okay, and and then it just it's standard. So what you get is like this way. Okay, and this is equal to alpha K, and this is equal to 1 minus divided K. Okay, so therefore this is equal to D0 sum of 1,000 of 2dk, 1 minus 2 and 1 dk. So by the way, so here I use the fact that the U dk is also real in this assumption. So without the cancel delta is the UK is equal to square root of EK plus EK and EK is equal to one divided by 3. Is what I use. I mean, it's just you just use that motivation over each hand to get this. So it's also a little bit of it. Sorry, I think again I was able. Okay. So you might notice. So now we do the same trick. So this is the case. The other, so last time I used the function that C equal to some number that dk divided 2 from k minus 3. So I use from here, I just approximate this is equal to product of d of this one. To this from E. So we will use the same trick here. We use the same trick. And then, so this is thin shell. So D of epsilon is the approximately D of permanent. So we use the same trick. So we use so this is the dk is okay. Is inside of this in part. So which means that so we use the same thing. So if you use the same trick, and then we notice that 1 minus 2 and above is from k is equal to cash or better is from k divided by 2. And if we use this equation that we use in the form. So then like this. And then I call this one equal to G. I call it this one equal to G. So this equation is yeah. So that's crazy. So I use this relation. So it's from I use this one and then plug this one into here. Plug this one into here. And then you get it. Okay. now, so this is called capital cushion. And using this one, so I can just, so capital cushion. So you can solve this capital cushion in terms of delta and use temperature, right? Beta has a temperature. Is that okay? Delta has, so from here, one can just have a relation between delta, deltas. And then it behaves like this one. So delta, and this E, which is the critical temperature, and this is the optimal, and it behaves like this. So that's not so dimension, so this delta is the order parameter superconductivity. So if delta becomes zero, which means there is no superconductivity. So when below the critical temperature, the state has a superconducting state, and then this T equals to zero, we can have the maximum order superconducting order. Okay. So first, let's consider what we try to determine T. Try to determine T, what we need to do is that the order temperature, so this order parameter becomes T. So therefore, as a TC, what we have is the first, number one, determine. From here, what we can do is determine TC. Number two, determine delta V. And then, and then number three, and then other T, when TC is very small. Of course, T is less than TC. And how delta of T for the function is respective. So we will ask the three questions. I mean, this is numerical, you can solve numerical. It's very easy to solve. I mean, just put the mathematical. I mean, you can just, okay. Anyway, but for this behavior can be just obtained by analytically, by okay, let's do that. Maybe I can show them. Okay, so the number one. So number one, to determine TC is actually delta equal to T. Set the delta, set delta equal to 0 and solve it. And solve gap equation. Gap equation. That's it. Okay, so that's the first thing. So this is equal to G. And then DC H E over 2 T C divided by and then we assume that the KB C is much less than H block omega. So this is a function. Okay. And then what we can do is that we use the form expansion. Okay. So later I use this partial x1 2 is sum over okay, and plug down the here. And plug this one into here. What you get is this one into the G and the E sum over 2AB C that curve C curve where the L equals to 0 to infinity, not H W. Where each of n is equal to n plus 1 x b. This is primarily one for 3. I don't get it. So in any case, this is the expansion. So the odd number here is equal to the equal per. And then we just perform the C integral. So perform the C integral, and then what you get is that the then so what you get as follows. So 1 is equal to 3. C times sum over n equal to 0 and 0 2 5 to C divided by A squared. Where the so kind of cut off because of this assumption. So we assume that the KBTC is much less than h bar omega d. So therefore, if n0 is the ground distance, so it's already enriched. So you can calculate the information by the and then this is equal to this is equal to G times sum over n equal to 0 and 0 over those two sources. Okay, so it's equal to 50. And so from here, 0, each bar omega 3 divided by 200 okay, and then if you do the approximation of this one, this is roughly speaking, G times log of 4E gamma density. And the gamma is called order constant, order macro constant, which is 0 to 1,500 feet long. This is the order constant. Okay, from here, on the term of KTC, if we were 1.13 H bar omega 3, and the E is given the correlation. Okay, perfect. So now let's look at this result. I just did some tricks to do that calculation by using tangent of axis to the expand distance and truncate the integral by assumption of this, and you get this result. And first of all, if G is very small, attraction is very small, you can easily check that this assumption holds. Is that okay? Because if h bar omega t is the divided sheet, and then e to the minus 1 over g, if g is very small, this is very big, e to the minus 13 quantity is very small, and it's exponential small. So therefore, KBTC is the exponential small of divided sheet. Okay? And also, again, so to get the TC, you have an e to the minus 1 over g, right? Which means that you cannot use perturbation theory to derive this critical temperature. So therefore, so this in any case, this is very typical in superconductivity. You cannot use the perturbation theory to derive the superconductivity. So there's a really quantum effect, non-product quantum effect. So this means that the superconductivity, so all method we learn is the superconductivity is due to non-product quantum. That's the main message this calculation tells. So in the quantum field, so all the quantum field you learn in college is everything perturbation theory. Even if you take QFT1, QFT2, all the calculation you do is everything is perturbation theory. You never encounter in the college physics non-particle quantum effect except the superconductivity. I mean, if you go to advanced university like Harvard, maybe Princeton, maybe you will learn some non-particle effect in like Statistical and so on. You will learn in QFT2 or something like that. But otherwise, this is the simplest, like I would say the most familiar physics, quantum physics you encounter in non-particle effect. That's why very important. Okay. Okay, number 2. What's delta? Okay. Sorry. What is that? Okay. This means that it's step equal to 0. And step equal to 0 means what? So where's the application? The application here. The application is okay. So beta is equal to 1 over KBT, right? And so this goes to T goes to 0, T goes to beta goes to infinity, right? What's tangent of infinity? 1. Good. If you put the tangent to infinity, so you have to solve 1 is equal to G. 0 h bar omega e dt. So this is equal to G L inch inverse delta zero. And from here, what I show is delta small is h bar omega t divided by inch one h. And this is equal to h bar omega t and e divided one h. If you assume this is the G is very small. Okay. Again, we have the E is minus one over G, H bar omega theta. So this is equal to 3.54 divided by 2 then therefore, critical function is proportional to this delta. Yeah, all that. Okay. Okay, and then let's go to number 3. In concept number 3, we use the following trick. So we use the this equation. So let's do. So this equation. Number of the size equation. And another equation is this equation. No, sorry, not this equation. Sorry. The original gap equation. Original gap equation. Original gap equation. So, and then after number 3, where we still hey, so this calculation is very similar to what I have done now. So, in fact, number 3, we do like this or this. Then what you get is 0 is equal to G, and on the same spot, we got 3, we got 3, C, and then punch. The expired is 0 like that. The square divided by 2, divided by 2 times e squared plus e squared, delta squared, and minus times d divided by 2 divided by 2 times d. Okay? Is it okay? Okay, and you use this one. Then we use this expansion. Use this expansion and find the sum by using this assumption. Then what you get is a false. I'm not trying to think of everything. It's just it's not so difficult to do. And then now we don't need G here because G is irrelevant. And then what you get is like this. I mean, it's just a calculation. Yeah. I mean, it's just before the time, so this so n is the 2n plus 1 of pi a dt and dt. So here it's from n prime is the same thing, 2 pi 2n plus 1 pi a dt, like this. Okay, and you just need to solve this equation appropriately. And then I'm not going to do all the calculations. I mean, it's just that everything written in lecture notes. And it's so, like, I mean, it's just approximation to the yeah. So, yeah, I mean, essentially, you can lift the student as your prime is the same as the upper bound of 10, and do the summation by giving sum of the odd number in n plus 1 square cube n equal to 0 infinity, and which is the which is something 7 times the number 3 divided by 8 and so on. And if you use that one, and you just got it, I'm not going to write down everything. So then this one, t delta square is equal to 85 squared. Anyway, so some number, and it's t minus t divided by t. So that's what she gives you. Some number, some irrelevant number. Therefore, so around here, around here, growth is t minus t curve around the proportion. Then those are the behavior we see in the near the grid. Any questions at the moment? Okay, then the last 20 minutes, I'm going to talk about density state in the component in the state, where the green function is very well. That's why I just spend time in the green function in the answer. Any questions at the moment? Okay. Now I'm going to write on here. Yeah, because I can raise. Yeah, I think I can read that. Okay, so let's recall of the propensity of state in the superconductivity. Propensity of state. To that, we use so-called recalibrate function. So we thought of this recalibrate function. Function. So T or sigma in T is in fact given by minus I A star and a T and then sigma T star. What how we define in the green function? So sigma is not. This sigma is the speed variable. Sigma. And then also we derived the spectral functions of sigma. Okay. A long time ago, I don't know, like 2 or 3 lecture before, we derived this. And using a Lemon spectral decomposition. So we derived it. If you look at the imaginary part of this resulting plane function, it is in fact proportional to the spectral function. That's what we thought. Okay, so that's what we thought. And then in the free field, we can just have the so free field. We already showed up the G R with K omega. It's just on one under H plus omega plus C K plus I A or delta, whatever it's called. I mean, delta is just compositional function. In previous lecture, I called delta or something. Delta. And then if you plug this one into here and look at the imaginary parts by using the 1 over x is equal to principal of 1 over x plus delta, something like that. If you use this relation I, sorry, x plus I, something like that. Yeah, as far as I know, is it correct? I don't know.
Minus
Delta x.
pi to get pi
Yeah. You guys have better than one. Okay. So if you use this so rho of k omega is equal to E over H star, and this is equal to delta E plus E plus G. Okay. So now it's just another function that E is equal to DK. So in the free field, and if even if the interaction included, so a dimension, so this is the whatever E, and the spectral function rho, and then here you have a dk, and you have a delta function like this one. So this is free field, but for interaction field dimension, briefly last time. Was in the lecture before, it's just in and out. For the integration, total integration is equal to. So with interaction, it becomes like this one. With the interaction. With interaction, but we will show that the with interaction, so if you integrate over this, the spectral function with by h bar, and this is equal to minus 2 imaginary part. And this is, if you look at the definition of this look at this, so this one is equal to roughly speaking. And this is equal to. So if you integrate all the spectral function, so all the spectral function, you should get equal to. You should get equal. So therefore, it means that so here you have one particle at the push energy equal to dk, but with the interaction, so the all. So this is me out, and then you've got it. You integrate by equal. So for example, it can be understood the density of state at the energy at a certain energy. Okay, let's compute the entire green function. The entire green function. It is superconducting segments. And let's call the thing about the upper spin, and C or upper spin of spin omega is equal to h bar, to infinity dt, and e to the minus upper omega t minus t. And the product of the upper one, and then we take upper one, down, and then plug dimensions many times superconducting state, the better operator is A and T instead of C. So I just change the base momentum. This is equal to UK and KT plus BK, deductive K, and U, deductive plus BK, deductive. And if you compute this one, what you get is that the integral of P to P pi omega t minus delta t And then we can start take the T. And then a semiconductor. Plus the square. And then the dagger. T and D. What you get? And now AK and EK are created the eigenstate whose energy is EK. AK and EK are related to eigenstate EK. So therefore, so this can be written like a E to the minus REK T divided by H bar or something like this. H bar. And this one is E minus K E divided by H bar and B. And then just do the computation ratio. And what you get is that this is equal to minus H bar. Your infinity E to the I omega T minus delta T, and you get current E to the minus I E divided by H bar. This is dagger. Plus minus E squared E to the I E divided by H bar. Okay, so that's what you get. We're going to use that version. Okay, so then perform the integration. And what you get is that the sorry, there is no minus sign. Sorry. Okay. So the performance, for example, rho spin K E over H bar is equal to 1.5 imaginary of G alpha of retarded green function, and this is equal to U squared. The answer is minus K plus E K squared delta E plus E K. Okay. So this is fine. So this you can easily see that this so this is coming from A diagram, and this is coming from B diagram. Okay? As you can see. So therefore, yeah, of course, this E minus PK comes from this part. This is of course A, and then E plus EK comes from this part, or from B. So therefore, this creates the quantum particle excitation, excitation. Whereas this one is more like a whole excitation. So then here, E is equal to minus EK, which is negative, right? So therefore, it just gives like whole excitation. Okay, that's what you have. And this is, as you can here see, so if you integrate over row k, so as I mentioned, so if you integrate like this is the DE, and if you can easily see DE into a row, this is equal to what? Can you tell? So if you think about D, into a spectral function by DE, what you get? What? Yeah, actually. So this is UK squared plus BK squared. Alright? This is equal to okay, so that's as we expected. Okay. And then so from previous calculation we already know UPS curve is equal to 1 half 1 plus CL okay, and VK squared is equal to 1 half 1 minus CK divided by E. Okay. And even if you look at this one, so you will see that the okay. And if you write down the so UK is something like this. So this is UK. UK square. And BK square is something like this. This is BK square. So therefore, CK is positive. So if you have a CK is positive, you have this the weight to the positive particle excitation is dominant. So this is a weight UK is dominant. Whereas the CK is negative, you have all excitation. You just get rid of the some state from the BCD component, BCD component space. This is side BCD. You just get rid of some states from it. So that is the problem. Okay, so that's what's going to happen, and I don't think I have time to talk about it. So next time I will talk about this equal to sum over K. So figure out the function and the K over them. We can do that. And this one, so this is empty state, and then if you use the yeah, that's what I call anyway. Okay, so next time I will talk about this density state and like at the beginning of this one, so you just sum over all possible moments on K. But here we need to be careful about which state you come over. Actually, this physical state or like this energy is greater than zero state will contribute to the density state, and we will balance out. Okay, so that's next time. Okay, so that's the first half of the recording. And unfortunately, I missed the half of the recording. unfortunately, that's the reality. Okay, so you guys should at least present here, so you guys are lucky. And the next time I will talk about a bit more about static fees and also how mindful effect and also that gives you the connection to Lamakin. So that's much more interesting in the next time. So let's go. Okay.
好理解。啊，这个我不知道会是这边是他们啥？我就你看一个可算它是那个然后在在那个就是长度附近，它的那个化学是不是长就等于？对，在这个附近，就是呼吸的零的时候，那个对比性的化学是不是在对比阶相对？所以它就应该是艾塔跟一减有这个是吧？它应该就是在于，那你就是它的对比的附近电脑认为才是。只是我不知道为什么现在对，因为那个我想看一看你要。我没上过。没有在课上翻译过，不好意思，我没法吸可以跑过。真的呀，人多演，我他妈做的都是啥？他那个场比较奇怪，我们做的都是不然他那个基础，不然他那个基础是报纸，对，那个这方面。你他妈，你什么时候你看到高的方面他妈是哦，对，刚那个我看那个关系然后这他为什么是高研究？这个我没搞清楚，我感觉他像是到2是吧？他那个他最高。
对呀，2。
但我是说这个但是他们或者是怎么
别人的分数没上错。
但突然多的又搞不着，就是贵，就是贵，那不。我也不知道他那我再来。你全是你们找不见了，完全两。我觉得没有品。
C 是。
自己就是1K， CK 等于1K 减，F 就是这个。这个是这个解释怎么样？
那你说是？
我说就是可以把那个起那个你们就是到底找不是后面到这个点你们一般是那个就是我都记了，考试中我也有一些节目出来。怎么回事？不是物理的那个。生活对，他是毕竟是这个球，我觉得应该是一个，就是考虑了那个小伙子是考虑的，然后最后一题是考虑了2，或者好像也是够不好的，那后面第3题这